This lecture is on section 2.2 of our textbook. And all we will do in this video is learn how to find the matrix representation of linear transformations. For now, we just say that there is a one-to-one correspondence between linear transformations from vector spaces of dimension n to dimension m, that vector space, and the set of m by n matrices. It's actually much more than a one-to-one correspondence, but we'll get to that later. But for now, just understand that for every linear transformation from V to W, there is an m by n matrix that represents it, and we're going to learn how to find that. The first thing we have to do is define an ordered basis. So far we've just said a basis is a spanning set for V, and it is the linearly independent. But now we're going to put them in a certain order, any order we want. But we have to have some order. So the standard ordered basis for R3 is E1, E2, E3, this, which is the ordered triples 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, we could order them this way if we want, but those are not the same ordered basis. For the vector space of polynomials of degree less than or equal to n, we will use this as our standard ordered basis, putting 1 first and x, highest power of x, last. We have to define what we mean by a coordinate vector. Let V be a finite dimensional vector space with the ordered basis consisting of vectors v1 through vn. For x in V, there we know unique scalars such that x, the vector x, is written as a linear combination of the v sub i's. The only difference here is that they're in some order. The coordinate vector of x is just the vector of coordinates. The coordinate of v1, the coordinate of v2, and down to the coordinate of vn. And notice how we write that. The coordinate vector of some vector in V is the coordinates of the ordered basis that you're using. The coordinate vector, what if x here happens to be one of the members of the ordered basis? Well, if it were v sub I, for example, its coordinate vector is 0 v1 plus 0 v2 up to 1 v sub I, and then the rest 0. So the coordinate vector for one of the vectors in the basis is just the vector of zeros with a 1 in the ith position. So now let T be a linear transformation from V to W, where V is dimension n, and you see beta there as its ordered basis. And W is dimension m, so here we have an ordered basis for W. Then for each j between 1 and n, there exists unique scalars, a sub ij, in the field for 1 less than or equal to I less than or equal to m, such that, such that the transformation on the v sub j is put into, well, it's put into this vector space W, and in W it has a unique representation in terms of the W sub I. So let's just say that one more time. If we take one of these basis vectors in beta and we apply the linear transformation T, we know that we get an element in W. and that element in W has unique coordinates that write it in terms or as a linear combination of the vectors in gamma. That's all this is saying. The matrix representation of T, the linear transformation from V to W, is the M by N matrix A, with the jth column vector being the coordinate vector in gamma for T of V sub j. And it's denoted by this, the matrix. So listen closely to the words. We're taking the vectors from beta and we are applying the linear transformation to those vectors, and then we are expressing them in terms of the ordered basis in W, and we are using their coordinate vectors as the columns in this matrix for T. Listen to that sentence a couple times, and then I think you'll see it when we look at examples. Here is a linear transformation from R2 to R3 given. Let beta and gamma be the standard bases for R2 and R3. So the first thing we do is we find out what does the transformation do to the basis of R2. So I want to find T of E1, and that is T of the vector 1, 0, and plugging 1 in for A1 and 0 for A2, we get the vector 1, 0, 2. And I need to apply the transformation to the second element of the ordered basis for R2, and that is T of 0, 1 then, and plugging A1 equals 0, A2 equals 1, we get the vector 3, 0, minus 4. You check that. So we find out what the transformation does to the basis vectors. And now I need to express those in terms of E1, E2, E3, but they already are. This vector right here is simply 1 E1 plus 0 E2 plus 2 E3. So in this case, there's no work to be done. This is the coordinate vector for the basis, the standard basis of R3. All we're going to do is put them in as column vectors. So our matrix then is denoted by this, and we just take these and put 1, 0, 2 in as the first column, and 3, 0, negative 4 in as the second. And that is the matrix for the linear transformation T. Our second example is a linear transformation that maps the vector space of polynomials of degree 3 or less to P2 of R. And it does so by taking the derivative of the function from P3. So, again, same thing. Here's the ordered basis for the domain for P3. I need to know what does the linear transformation do to those basis vectors. And so I need to take T of 1, and that is equal to, the derivative of that is 0. I need to take T of x, and the derivative of x is 1. I need T of x squared, which gives me 2x, and T of x cubed gives me 3x squared. In an example this simple, we don't bother to write these out in terms of the standard basis of P2, but I would like to do so just in one case so you for sure see what we're doing. Let's take that one. T of x squared is 2x, which is 0 times 1 plus 2 times x plus 0 times x squared, writing it in terms of the ordered basis gamma. So the vector that we get from that, the coordinate vector, is 0, 2, 0. But you don't need to write that out to see it. You can just do it in your head. So we'll go directly to the matrix, call it A, the matrix that represents the linear transformation T using beta and gamma, the standard bases, and it will be, okay, so we take the first one and write it as a coordinate vector, a column vector in the basis gamma. So it is 0, 0, 0. 0, 1, 0x, 0x squared. The next one, t of x equals 1. Well, 1 is 1 times 1, 0 times x, 0 times x squared. T of x squared, well, we did that column vector. That's 0, 2, 0. And t of x cubed is 0 times 1 plus 0 times x plus 3 times x squared. And this is the matrix that represents the linear transformation 2. Notice that the dimension of P3, the dimension here is 4. The dimension of the range space is 3. So we have a 3 by 4, an M by N matrix, and that will always be the case. Theorem 2.8 we're just going to mention quickly and illustrate it with an example. Let U and V be finite dimensional vector spaces with ordered bases, beta and gamma respectively, and let T and U be linear transformations from V to W. This is just saying that if you have the matrix for the sum of the two linear transformations, it turns out to be the sum of the matrix for T plus the sum of, plus the matrix for U. And also the matrix for alpha T, where alpha is an element of the field, is the same thing as alpha times the matrix for T. Later, if we get that far, you will learn that this space, L of VW, is a vector space of all linear transformations from V to W. Right now, we know that there is a one-to-one correspondence between linear transformations and M by N matrices, but actually, the set of all linear transformations is a vector space. But we're not going to prove that now. It comes later. Here is an example to illustrate Theorem 2.8. If T takes R2 to R3, and so does U, we have the rules for them here. T of A1, A2, U of A1, A2. We can get the matrix for A. In fact, we already did. That was 2 slides back. We got this matrix for the linear transformation T. And you do the same, this one right here, and then you do the same using U and get the matrix for U. You should put this on pause and make sure that you can get both of those matrices. Now, just add the 2 matrices together, and we get, according to Theorem 2.8, we get the matrix for the linear transformation, which is the sum of T and U. So just to check and see if that's right, let's add T and U by using the ordered triples here. Add these ordered triples, and we get T plus U is the linear transformation that takes the ordered pair A1, A2 to this ordered triple. Just added the coordinates in the 2 ordered triples. And now, if I see what does it do to 1, 0, what does it do to 0, 1, I get these 2, and I drop them in as column vectors, and yes, I get exactly the same matrix. I'm going to do one more problem. This is number 5B in the text. I thought it would be good to do a problem where when we apply the transformation to the ordered basis in the domain, we don't come out with the column vector right away. You have to express it in terms of the basis gamma. So this one is taking P2 to the 2 by 2 matrices, and here's how it does it. Give it a polynomial, and this is the rule for finding the entries in the 2 by 2 matrix. We want to compute the matrix for this linear transformation. So again, we see what it does to the basis vectors in P2. So we calculate T of 1, and going by the rules here, f prime of 1 is 0. 2 times f of 1 is 2 times 1 is 2, and we get 0, and of course the second derivative is 0. T of x is, and you check this, 1, 2, 0, 0. T of x squared is equal to 0, 2, 0, 2. So we have found the image in M of the basis vectors. Now we need to express those in terms of the basis, the ordered basis gamma, in order to know what their coordinate vectors are. So, well, I'm going to take a sec here and call this, I don't want to write these out, let's call this E1, E2, E3, and E4. Okay, so now going back and writing this, I have then 0E1 plus 2E2 plus 0E3 plus 0E4. The second one, I have 1E1 plus 2E2 plus 0E3 and 0E4. The third one is 0E1 plus 2E2 plus 0E3 plus 2E4. So now we have the column vectors. And the matrix for T relative to the ordered bases beta and gamma given is equal to, well, let's just drop these in. 0, 2, 0, 0, 0, 2, 0, 0, 1, 2, 0, 0, and 0, 2, 0, 2. So the first thing you do is write down your two ordered bases. You know your matrix is going to be a 4 by 3 because M here is equal to 4, N is equal to 3. We did get a 4 by 3. You first find what the linear transformation does to the basis vectors in beta. You get those results, and then you write those results in terms of its ordered basis in W, and therefore you get the coordinates of its basis vectors, and you drop those column vectors into the matrix in order, and that is your matrix for the transformation.